VSEPR, which stands for Valence Shell Electron Pair Repulsion Theory. Sometimes we say VSEPR. Not quite right, I guess, right? But VSEPR. Here we finally get to the shape or the geometry of these molecules, what they would actually look like. Because, it's found, for example, that CO2, carbon with two oxygens, they're in a straight line. They're a linear molecule. Well, water, H2O, again, 3 atoms, it's not. Water's actually bent. Looks like a V, where CO2 is a straight line. Why? What could account for that difference? VSEPR will allow us to correctly predict the geometries of these molecules. All right, here's the simple thought behind it. You have all these electron pairs. The electron pair could be a lone pair. It could be a bonded pair. Right? They could be single, double, triple bonds, that kind of. But they're always these things that are coming off this central atom. But they're all these electrons, and electrons are negative, and they repel from each other. And so these bonds, or these lone pairs that are coming off of the atoms, they're going to be trying to get away from each other as far as possible. So they're going to spread themselves out. How far can they do it? And keep in mind, we're talking about 3-dimensional molecules here, not just 2. Right? But if we can figure that out and see, hey, a lone pair here and a bonded pair here, and spread them out, we'll correctly predict the geometries. It's really pretty much that simple. We got some names that go along with it. You got to be able to recognize the 3-dimensional geometries. All right, so let's start with, again, this idea of the electron geometries first here. Here's a table from the book which shows us how we can spread these things around. So let's say we've got 2 things coming off our central atom. They're using this molecule here, Be with 2 hydrogens. This is an electron deficient molecule, right? So 2 things are coming off. But CO2 would be the same kind of a thing. CO2, you have a double bonded oxygen, a double bonded oxygen, 2 things. I don't care if those things are single bonds or double bonds or lone pairs. Doesn't matter. Just count how many things you have coming off that central atom. So in this case, again, BeH2, you got 2 things. A single bond to this way and a single bond that way. So you think about that. How can I get 2 things away from each other as far as I can? They're going to repel because they're electrons, right? Well, 180 degrees. Right? That's as far as I can get them apart. I would call that a linear molecule, and the angle is, again, 180 degrees. What if I had 3 things? So here they're using BH2, boron with 3 hydrogens. Another electron deficient one, but there's other examples. Formaldehyde would be one that would have 3 things coming off a central atom. How far can I get those things apart? Well, 360 degrees in a full circle. I guess 120 degrees each way. That's as far as I can get them. But if I get them really closer, then it's going to be less than 120. They're going to be cramping each other a little bit there. Also, this will be flat. This will be all in a single plane, those 120 degrees. Because if I tried to bend one of them up, that's actually getting closer to the other ones. I don't want to do this. It gets closer and closer, right? I want to keep them flat. And so I'm going to have those 3 things all in the same plane at 120 degrees away from each other. And so there's the picture of that right there. And what is its name, that arrangement? Trigonal planar. All right, it's planar, it's flat, and trigonal, triangle, 3, right? And all the angles are 120 degrees. Makes sense so far. 4 things. What if you have 4 things coming off that central atom? Here, CH4 is the example they're using. 4 things in 3 dimensions turns out to be what's called a tetrahedral. Tetra meaning 4, right? So a tetrahedral looks like that. It kind of looks like a tripod. See 3 legs going down and then one going straight up from the center. Tetrahedral. The angles are 109.5. Actually, it's 109.47. Actually, it's the inverse sine of a negative 1/3 in radians. But anyway, you could just remember 109.5. That's the angle between any 2 of these things in a tetrahedral. Right? Angles are 109.5. Tetrahedral is its name. Here's 5 things and 6 things. Before I jump to there, let me show you a PhET thing here, which is really helpful to see what these things are. We just did the first 3. We did linear, and that's what I've got right here. I've got this purple right in the middle, and I've got 2 things that are coming off of it, right? And so you can see if I rotate this around, that is a perfectly linear molecule, and like they've marked, it's 180 degrees. If we take another thing and put it on here, there we go. Here I've got 3 things. Again, this is as far as I can get them. You can see they're totally flat. They're in a perfect plane. And if I look down onto that plane, they're spread out by 120 degrees each. This is a really cool little simulation that I would highly recommend you play with here to get an idea of these shapes. Let's do 4. Bring it on. Here's my tetrahedral. Kind of looks like a jack maybe or something like that. I don't know. But I like to think of it as a tripod. See, if I orient it this way, it's kind of like I've got this middle, then I got 3 legs coming down, and the 4th spot is going straight up the top of my tripod. Another way to think about this is like a V going down. Here's a V going down and then a V going up. But you can see they're rotated by 90 degrees from each other. However you want to think about that. I like the tripod idea. I don't know if my brain can just kind of picture that the easiest. Whatever works for you though. And you see that the angles are 109.5 for this tetrahedral. Okay, looks good. Very helpful, this little diagram or this little PhET simulation, like I said. Definitely play with it. Let's go on. What if you had 5 things? 5 things. This one is the most unusual. What it looks like is take one of these trigonal planars. Now, take it and turn it on its side so that we're seeing it here. See, here's my phosphorus with a fluorine going to the left, and then 2 of them going to the right. One of them is coming out at you a little bit. The other one's going back away from you a little bit. This solid dashed wedge comes out of the paper towards you, whereas a solid dash. Is that what I said? I mean, a solid wedge comes out at you like this, where a dashed wedge like this one going up here goes back into the paper away from you. Okay, and so if you look at just those 3, you would have this, a trigonal planar. They're all flat, they're in the same, and there's 120 degrees between them. But then from this planar one, then you got another fluorine going straight up from the middle, another one going straight down from the middle. That's this top one up here and this bottom one right there. Okay, so a grand total of 5 of them going off. They call this arrangement trigonal bipyramidal. Trigonal because, okay, 1, 2, 3 right there in the middle. And then bipyramidal because there's like 2 pyramids. One's going up to this peak, the other one's going down. It's kind of like an upside down pyramid going down to the bottom fluorine as its peak. This is the only one that actually has 2 different types of angles. We have the 120 in the planar part, and then you have a 90 degrees for the one going straight up or straight down. That's 90 degrees. And so if we go over here to the PhET diagram and the PhET simulation, and let's add another one. Here we go. This is my trigonal bipyramidal. And again, if you look at this, I've got, see these 3, 1, 2, 3 that are in a plane. They're perfectly flat. And if I tip it down like that, if I look kind of down that axis, there you see 120 degrees between them. So planar, 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 those 3. And then, so if you look at that plane, then you got the one here going straight up and the other one going straight down. And it shows here those are 90 degrees from each other. So 2 different types of them. We call these the equatorial ones, these 1, 2, 3s, because they're in the middle, the equatorial plane. We call these the axial because they're kind of like on the axis, if you will, the up and down axis of this molecule. Okay, there you go. Trigonal bipyramidal is its name. All right, lastly, what if you have 6 things coming off the middle? 6 things, it's kind of just like this, but instead of a trigonal in the middle, you get a square. 4 things right through this planar part, and then 5 and 6 straight up and straight down. That's called an octahedral. If you think about this, everything is exactly 90 degrees. This is a nice symmetrical arrangement again, and if we do that here, let's add our 6 things. There we go. You see the 4 that are in the equatorial plane, 90 degrees from each other, and then straight up and straight down. No matter how I rotate this, I've got 90 degrees all the way around. Nice symmetric type of thing. So that's the best way to arrange 6 things. Okay. These are the basic shapes, if you will, or the basic arrangements that you could have. Anywhere from 2 up to 6 things coming off your central atom. I guess you go beyond. You go to 7, 8, 9. There's almost never any need to, though. So we're going to stop right there. And it's only 5 shapes, but this is the first thing. You got to get down, master these 6 basic arrangements. They call these the electron geometries. electron, because notice they haven't cared what it is that's coming off here. It could be a double bond, a triple bond, a single bond, or a lone pair. It doesn't matter. It's just the fact they're electrons, they're repelling each other, so they call these the electron geometries. And this is the very first step for any molecule, is just to figure out which of these 5 basic electron geometries does it fit into. Okay. Then the second step is to realize that if you have one of those spots occupied by a lone pair as opposed to an atom, well, the lone pair of electrons is just part of the wave, part of the wave function, right, of the electrons surrounding that central atom. It's not like a whole big new atom coming off and giving a part of the geometry. It's just electrons in their waves. You can't even see them. They're just little teeny tiny electrons as opposed to these great big atoms which are actually attached. You see, if I want to talk about the actual molecular geometry of the molecule itself, all I want to think about is the atoms, not those lone pairs. And yet, those lone pairs take up room. They take up one of those spots in one of those 5 basic arrangements. And so that's the next step, to figure out where the lone pairs are and how does that affect my molecular geometry. Again, the molecular meaning I'm only looking at the atoms that are making up that molecule. All right, so again, always start with the full electron geometry, one of those 5 basic ones, and then go from there. Here's how that's done. If you have a linear molecule, if you put a lone pair in one of those spots, like one of those X's, make it a lone pair instead, well, you know what? It's still a linear molecule, right, if I just can't see this one. So that's pretty boring. They don't even put an entry on there. Let's say I had 3 things, trigonal planar, and then instead of XXX, 3 atoms, I put one of them as a lone pair. So there it is. Now, if I can't see that, if I make it invisible, in other words, think about it that way, what am I left with? I'm left with A with 2 X's coming off of it, but they're not linear. They're coming off at 120 degrees. How do I know that? Because this was derived from that basic geometry of a trigonal planar, which had 120 degrees. If we look at the PhET diagram, maybe this will clarify it. Let's go back to a trigonal planar. So there we go. They're all in the same line. This is like the AX3 over here. Right, the AX3, the central A with 3 X's coming off of it. All right. Now, let's replace one of these with a lone pair. So I'll remove one and then I'll add a lone pair on instead. Alright. Now you see this atom, and this lone pair are still in a plane. They're perfectly flat and they're still at roughly 120 degrees. There we go, 120. They're not showing it for here because, again, that's not an actual atom. That's a lone pair that's still taking up that spot, but it's not an actual atom. Okay? So there we go. It comes from a trigonal planar, but I can't see this top. And in fact, this program even lets you remove it. It says show the lone pairs. If I remove that, I can't see the lone pair. It used to be right there. If I was to actually look at that molecule, this is what I would see. 3 atoms connected like that at 120 degrees. And I'd be scratching my head saying, why isn't it out here? Why aren't they 180? Why are they at 120? Because I've got this invisible lone pair. Let's display it again. There it is, taking up that 3rd spot. Okay. So again, the molecular geometry, if I look at that, I say, all right, what do I have here? I'm going to just call that a bent molecule. Sometimes you call it a V because it looks like a V here. But a bent, I think that's more common. A bent molecule, and it's bent at 120 degrees. So again, this PhET diagram is nice. This PhET simulation, the electron geometry is trigonal planar. We knew that. The molecular geometry is bent. And it's not just bent, it's bent at 120 degrees. I like to include the angle there because that is important. Let me show that. All right. Let's move on. What if we have a tetrahedral? Oh, by the way, if you go back up here and replace the other 2 of them, so you got 2 lone pairs, you're left with just an AX. That's just linear. That's kind of trivial. All right, what if we start with the tetrahedral? So 4 things coming off it, and we replace one of them with the lone pair. So here we go. Now you've got these 109.5 degrees as usual, but you can't see this lone pair on the top. You're left with a pyramid with a triangle base. And so that's why they call it trigonal pyramid. That's the molecular geometry. And again, the PhET diagram, let's go ahead and do that. Let's start with 4 things. There we go. There's my tetrahedral, 4 things. My tripod, if you will, with the thing going straight up. And I remove one and replace it with a lone pair. Alright, so I've still got those 4 things. It's still tetrahedral, essentially. I've got my triangle, the 3 legs of the triangle, and going straight up is my lone pair now. And again, if I remove the lone pair from the display, just make it invisible. It's still there, but it's invisible. This is what I'm left with. And this is, well, kind of a squished pyramid, but all the same, this is a pyramid. I can rotate it around here like this. But this is a pyramid with a triangle base coming up to the peak there at that purple central atom. It's a pyramid. Again, it's got a triangle base, so if I look straight down on it, there's my big triangle. That's what the base of this pyramid looks like. So trigonal pyramidal is the molecular geometry, but it comes from the actual original tetrahedral electron geometry. And again, if I display the lone pair, there I can see all of them. All right. What if I did 2 lone pairs? So here's the first one here. I did a second one. So it's still a tetrahedral, but 2 spots are now being taken up by a lone pair. Well, let's say that's another bent molecule, but this time it's bent at 109 degrees, where before it was bent at 120. Again, I can do that over here. We'll remove one of those and replace it with a lone pair. And there we go. It's still kind of a tetrahedral because there's 4 things coming off it. There we go. Electron geometry is tetrahedral. But the molecular geometry, if I make those lone pairs invisible, because I say, hey, I can't really see them, I'm left with a bent molecule. But this time it's not bent at 120 like before. This time it's bent at 109.5 because it came from this tetrahedral. Cool. All right. Again, if I do a 31, trivial linear kind of a thing. All right. Let's jump down to the number 6 and we'll come back to number 5. Okay. Number 6. If I start with octahedral, I put 1 lone pair in it, I'm left with a square pyramid. If I put 2 lone pairs in, I'm left with a square planar. 3 lone pairs T-shaped, 4 lone pairs linear. Wow, what's happening here? Okay, let me go to the PhET diagram here and maybe show it that way. 5, 6. Okay, so here's my octahedral. Starting off with, there's my 4, the square kind of planar part in the middle. Take one of them off and put a lone pair on instead. So there it is. I'm going to rotate it this way actually. I prefer putting that lone pair on the very top. It doesn't really matter, but that's just the way I like to think about it. So I've got my 4 in the planar, 1 straight down, but my lone pair is up here, or if you want to prefer it this way, down here, however you want to think about it. Alright, if I make it invisible, what am I left with? Oh, I see. This is another pyramid. Goes to the peak here at the top, but this time this pyramid has a square base, like that. So square pyramidal is its molecular geometry. The electron geometry is still octahedral because, again, it's really down there, and so I got a grand total of 6 things coming off of it. Alright, so square pyramidal, everything's 90 degrees. What if I replace a second one with a lone pair? Now, you can see that the 2 lone pairs are opposite each other, and the remaining atoms are in this square planar part. If I make them invisible, it's really obvious. It's a perfectly flat square, right? So square planar is the molecular geometry. Now, note, why did they put the lone pairs opposite each other? I mean, couldn't I have put it like maybe at this position instead? Yeah, sure, but then my lone pairs would be 90 degrees from each other, as opposed to this way where they're 180 degrees. And see, because lone pairs are out there by themselves, they're not bonded to another atom. Lone pairs actually have a touch more repulsion than a bonded pair. So you want to get them as far apart as possible. If you got lone pairs, get them as far apart as possible, and 180 degrees would be it. So that is the correct arrangement. You got to put them opposite of each other like that. Alright, let's go for 3 lone pairs. So take an atom off, add another lone pair. Alright, there I still have my original lone pairs, and they put the other one just right there. So now that's what I've got. If I make those lone pairs invisible, what am I left with? Well, it looks like a T, doesn't it? Oh, a T on its side. There. It looks like a T, right? And so it's T-shaped. A T-shaped molecule came from my octahedral like that. T-shaped molecule with, what are my angles? 90, 90, and I guess technically over here 180 going all the way across like that. Alright, what if we did one more? All right, one more. Again, they're going to put them opposite of each other as much as possible. I think that's pretty clear that the molecular shape is now linear, straight line. Looks like that. All right, so this chart does make a lot of sense, I think. We went from octahedral to square pyramid, square planar, T-shaped, linear. And again, on these two, make sure you get the electron lone pairs as far apart as possible. All right, now let's go back up to number 5 here. We start with a trigonal bipyramidal. We put a lone pair in. Look what they did. They put the lone pair in the planar triangle part. They did not put it in the axial part. That's correct. But why? Because again, lone pairs repel more. In the planar trigonal part, they're separated by 120 degrees from position to position. Whereas in the axials, they're separated only by 90 degrees. So they're a little more cramped. If you're trying to get these lone pairs with their extra repulsion as far away from other plugs, you gotta put it in the trigonal planar spot, not the axial. So they did it absolutely correctly, like here, putting that lone pair right there in there. And let's go ahead and do that here. Let's take these lone pairs off. We'll add, there we go, 5 things. So here's my trigonal planar. Again, in the middle there, 1, 2, 3. So those are in a flat plane if I rotate it around. And then my 2 axial spots. Let's see if I can orient this more a little better. There we go. My axial straight up, straight down, and then those 3 in the planar parts right there. Okay. If I remove one of these and add a lone pair, it correctly put it in that trigonal planar part. It did not put it up here. It did not put it down there because those are only 90 degrees. If I look straight down on it, it put it in here where it's 120 degrees from neighbor to neighbor. That's the right place that you absolutely have to put it. Okay. Now, what does that do for my molecular geometry? I know the electron geometry is still trigonal bipyramidal. If I make those invisible, what am I left with here? They call this a seesaw. Well, let's see. If I rotate this and put it down like that, let's see if I can get that. Maybe it looks more like a seesaw now. It's kind of hard to rotate it very well, but you get the idea here. It's kind of like I have the 2 legs coming down here that touch the ground. Then I got my straight board, and it'll rock back and forth like a seesaw on a playground for kids. So a seesaw. I've got 120 degrees here. I've got 180 degrees here. And then from here to here, I've got 90 degrees. So I actually got 3 different types of angles in a seesaw. But it makes sense. That's what I get. All right, so let's orient to the axials. Go straight up again. What if I remove one more and add? I put it again. It goes right in that trigonal planar spot, not the axials, which is correct. And if I make those invisible, I'm left with another T molecule again. All right. Let's do one more. Remove that and replace it with the lone pair. It correctly put it in the trigonal planar part. And molecularly, what excuse me, molecularly, what am I left with? Linear, 180 degrees. All right. So I really encourage you to play with the PhET simulation, understand these geometries, understand their names and the angles and where the lone pairs have to be. It's a really powerful, simple, and yet powerful theory that correctly predicts the shapes of these molecules and the angles that their bonds, that the atoms are connected to one another. Very, very helpful. All right. Here are some real-world examples for you that I've come up with, the electron geometry and the molecular geometry. Carbon dioxide, there's the Lewis structure. You see that central carbon has 2 things coming off of it, a double bond to the left and a double bond to the right. So that's going to be linear. BF3, that was one of the examples we already saw, trigonal planar. Ammonium, NH4+. 4 things coming off of it, so it's going to be tetrahedral all around. Water, I already mentioned this. There's the Lewis electron dot structure. You see there's 4 things coming off, so the electron geometry is tetrahedral, 109.5 degrees, right? But if I make those lone pairs invisible, if I only count the atoms, I'm left with a bent molecule. And it's bent at 109.5 degrees because it's from the tetrahedral. Oh, by the way, technically, water's not bent at 109.5. It's more like 105 or maybe 104.5. It's not 109. It's actually pushed in just a little more. Why? Because again, lone pairs repel more than bonded pairs. And so It might start off at 109, but don't forget I got a lone pair up here and another lone pair, and they're going to repel, and they're going to actually push the angle of those atoms and tighten them, pinch them just a hair. And so technically it's not 109, it's more like 104 and a half. And actually, if I go back here to the FET and let's see if I can restart this. There we go. Go to real molecules this time. And, oh, I could have just done it up here. I see that now. Okay. Oh, good. It came up with water. They got a lot of these already programmed in, which is nice. All right, but we're going to choose water. Let's show those bond angles, and let's see the names of these guys. So, tetrahedral and bent, just like I showed you. But there we go. You can see if I take those lone pairs away, there's my bent molecule, and they've done it correctly. Yay, 104.5 instead of 109, because those two lone pairs sticking up here are actually pushing those bonds for the atoms a little closer together. So they've done it correctly. Yay, that's a good job. All right. SF4, there's the Lewis structure for it. You can see it's going to be 1, 2, 3, 4, 5 things coming off that sulfur, so trigonal bipyramidal. One of them is a lone pair. If I make it invisible, I'm left with a seesaw. Okay. And here, XEF4. Noble gases can make compounds. Here's an example. Here's the Lewis structure. 6 things coming off, so that's going to be an octahedral. But 2 of them are invisible because 2 of them are lone pairs. That'll give you a square planar. All right. So lots of practice on those should help. Lastly, polarity and dipole moments. Remember, a polar bond is one where the electrons are not shared equally. It's lopsided, right? One of the atoms gets it more often, so they become partial negative. That's talking about just the bonds. In a molecule, you've got these shapes, right, with 4 or 5 things coming off of them, and maybe you have a polar bond going this way and a polar bond going that way and a polar bond going that. If I step back and say the whole molecule, is the whole molecule lopsided? Right? Does the whole molecule have a partial negative side and a partial positive side? Right? Is that predictable? Can I learn that from looking at just the individual bonds? I understand the individual bonds can be polar, partial negative, partial positive, based on electronegativity. But when I step back, what about the whole molecule? And see, that's important because when this molecule is going to be interacting with other molecules, it's the whole thing that interacts. It's not just an individual bond. So I've got to be able to answer this question, is the molecule lopsided? Is the molecule have a partial negative and a partial positive? Okay. Now, to get at that, you have to look at the shape, the molecular geometry. You have to look at where the lone pairs are. You've got to look at if the individual bonds are polar. And finally, are they additive or are they do they cancel each other out when you look at the entire molecule? There's a lot you got to go through to get to this answer. But let's do it. Let's say you had an HO bond. The oxygen is more electronegative than hydrogen, so yes, this is a polar bond. All right. Well, water is H2O. So you've got 2 of these bonds here. One of them points up towards that oxygen. The other one also points up towards that oxygen. But they are at 109.5 degrees from each other. Remember, because water comes from a tetrahedral, right? And those 2 lone pairs. All right. So if you want to think about like sticks pushing on that oxygen in the middle, maybe something like that, all right? Or a tug of war kind of a thing, or something like that. One of them's pushing on it here. One of them's pushing on here. If you did it at the same time, do they cancel each other? No, actually, because this one's kind of pushing upward. This one's kind of pushing upward. Maybe left and right it cancels, but they're both pushing up. And so overall, it's going to push straight up right through the molecule, as I've indicated right here. See, this, if you think about vector addition from math, if you will, in geometry, these 2 vectors would add together to give you an overall vector. All right, straight up. Or like I just said, the thing of it sticks, this pushes up, this one's also kind of pushing up. Overall, I could represent that by a single stick, if you will, pushing straight up, right through the oxygen, right through the middle, spatially, of those 2 hydrogens. That's your overall dipole. Since that does exist, it does add up to give you this overall dipole, then I would say water is polar. Water as an entire molecule looks lopsided. It's got a partial negative side up here, which is on the side of the oxygen, and it's got this partial positive side down here where the hydrogens are. All right. Now, see, I wouldn't be able to do that without knowing that it's 109 degrees, and so, because what if they were 180 degrees? Then this one pushes left, this one pushes right, and they exactly cancel each other out, and I wouldn't get any net dipole. In that case, if they were happen to be 180 degrees, then yeah, it would be nonpolar. There'd be nothing lopsided about that molecule. Because they don't, because it's at an angle, water is polar. All right, so here's the exact example of what I was just talking about, carbon dioxide. Oxygen is more electronegative, so it's pulling those electrons more towards that oxygen. On the right side, it's pulling towards that oxygen, so this is like a tug of war. One's pulling this way, one's pulling that way, but they're going to cancel each other out when I put it in the whole molecule, because they're exactly 180 degrees. There's the Lewis structure, only two things coming off that carbon, right? So at 180 degrees, they cancel each other, and CO2 is non-polar. There is no overall dipole, non-polar. Okay. Whether something is polar or non-polar has a huge effect on the way it's going to interact with other molecules, what it's going to be soluble in, how it's going to behave in the body. It's one of the big properties that a molecule can have, whether it's polar or not. One last example, SCN, we already did this. There's the Lewis electron dot structure. You see carbon does have two things, so it is linear. It is 180 degrees. But in this case, I've got the pole to the nitrogen in one way, a pole to a sulfur in the other way. And while nitrogen, compared to carbon, nitrogen is the more electronegative. And over here, sulfur is the more electronegative. Nitrogen is the larger one. Nitrogen is definitely more electronegative than sulfur. So if you want to think of it, I got a bigger arrow pointing towards the nitrogen, a smaller one pointing towards the sulfur. So overall, that's going to add up to one going directly towards that nitrogen. And actually, let's look at those electronegativity values. Carbon, yeah, that's what I was thinking. Carbon is 2.5. Sulfur is actually 2.5 as well. And so this should actually show no dipole. Just a minor correction, but go ahead and remove it. No dipole going towards the left on the sulfur, dipole going towards the carbon. So overall, yeah, they don't cancel each other. It just goes towards the nitrogen. So when it's asymmetric as far as the atoms are concerned, you probably are going to have a dipole moment because they're not going to cancel even if they are at the right angles from each other. All right. Well, there you go. That concludes it. Now you know how to do the electron geometries, the molecular geometries, the names, the angles, and whether the molecule will be polar or not.